The title of my talk is Good Channels, the Bad Channels, the Ugly Channels. I actually stole that name from a person I met at the Advanced Probability, or the Applied Probability Conference. You'll see why I use that name in a minute. So, what are we actually talking about? This is sort of the only EE slide in the entire discussion. The sort of framework for our work is based on this spectrum sensing for cognitive radio. Cognitive radio, the aspect of cognitive radio that we're interested in is about figuring out how to get access to spectrum. Cognitive radio defines primary users and secondary users, where primary users are owners of the channels, and secondary users are people who are allowed to use the channel if the primary user isn't using it. The secondary user is not allowed to interfere with the primary user, and the secondary user has to sense and adapt. So this is the problem we're actually looking at. Spectrum. It's hard to get at, it's hard to come by, and using it efficiently isn't exactly easy. So for our framework, we're going to imagine that there's some n large number of channels, and we're going to imagine that we have a limited number of measurements, L, and that at each measurement interval, or whatever that is defined as, we can only measure one channel per interval. So spectrum, from a secondary user standpoint, kind of looks like this. It's got, its frequency is separated in this direction, and time is separated this way, and there are basically these sort of open slots. And there's these white slots and blue slots are used by the primary user, and white slots are not. And what the secondary user has to do is figure out some sort of a model for when and where there will be a blue space that they have to avoid. So if the secondary user had sort of a map of what the probability of finding blue chip was in any frequency at any time, then that secondary user would have a much easier time filling in the space. So what we're going to do is build that map. And the things we're going to need to do it are a test that classifies with the minimum number of samples and a hopping strategy for distributing the measurements. And you'll see why I need those two things in a minute. So this is sort of an outline of where I'm actually going. I'm going to try to formulate the problem a little better, give some motivation, and basically give a general discussion about hypothesis testing. Then I'll talk about, this will introduce the tool that I'm going to be using, which is the SPRT, and I'll talk about how to optimize the SPRT for a single channel. That is to get the number of samples I need down to a minimum, and then while maintaining some error bound. Then I'm going to build a hopping strategy with this tool for multiple channels. Then I'll look at some schemes that approximate for comparison. Then I'll check out some simulation results and look at a little bit of future work. So we'll take an analogy from the statistics textbook. Suppose I have a bag of unfair coins, and I want to figure out what are the parameters of these unfair coins. I'm only given a limited number of flips. How should I distribute these flips? When should I stop flipping a coin and say this coin is known well enough? When should I, can I find coins that are on one side or the other? And how does that, what's my strategy for distribution? So it doesn't down to the side, just a bit of notation. I'm going to name the parameter of the nth coin Pn. So this problem is actually sort of a little difficult to get at and requires a lot of samples to actually get right. So I'm going to try a different problem. I'm going to simplify it, or maybe complicate it a little bit depending on how you look at it. Instead of actually trying to determine what the parameter is for each coin, I'm instead going to try to classify coins. That is, I'm going to take a coin, flip it a few times, and then put it in a bin. Either a bin of really low probability of coming up with whatever, a bin of really high probability of coming up with whatever, and a bin of this takes too long and I don't really want to deal with it anymore. And so if I can create this binning of channels, or binning of coins rather, the secondary user, when he comes along and has this information, will have an easier time figuring out which channel to use once they know those parameters, or at least where they approximately are. So this slide's really busy because I have to talk about how the problem was solved. And this is the old solution, which is to use Neyman-Pearson notation. We define simple hypothesis. And the only things I really want you to see on this are, one, this is a likelihood ratio, and two, this is what I named the type 1 and type 2 errors. They're alpha and beta. So, what's our strategy? The sort of critical observation is that if I model my channel's occupancy with a Bernoulli random variable, the variance of that Bernoulli random variable is this, just by definition. So, if I look at the edges of this Bernoulli random variable's variance, they're relatively low. And in fact, they're lower than stuff in the middle. This is good for us because it means that if we can somehow prioritize things that are lower variance, then, or prioritize things with parameters that are on the edge, we get lower variance for free. Not exactly for free, but you'll see what we pay for it. And so, what I'd like to do now is constrain my attention to things that are on the edges, and that way, these things that are on the edges will have lower variance just because of the way this graph looks. Why do I need lower variance? It turns out that if I use the most basic estimator, the sample mean, the variance of the estimator is directly a function of the variance of the random variable. And so if I make the random variable's variance lower by picking the right parameter, then I get lower variance of the estimator just by sampling the right thing. Now, this is basically the driving force behind our idea, that if we can somehow prioritize things with lower parameters, or parameters that are on the edges, we get lower variance, and we can measure them, we can be more confident about our measurements in them with fewer samples.
Is M a random variable, capital M?
In general, yes. M is the stopping time, or, well, technically it's first crossing time, and you'll see, I'll define them more carefully in a little bit. So, if I'm going to classify, simple hypotheses aren't going to cut it. Instead, what I'm going to need is composite hypothesis of this form. So, in order to figure out whether or not, or in order to build a test for this type of hypothesis, I'll refer to a sort of cute argument by Abraham Wald. And the cute argument is this.
James, I'm sorry,
Yeah?
what's theta again?
A theta is just a generic parameter of a distribution. And so a specific notation that I sort of glossed over is that if I use theta, I'm talking about a generic parameter of a generic distribution. And if I use p, I'm talking specifically about the parameter of the Bernoulli distribution.
In this context, I think theta is a population mean, as it says.
Yeah, that's what it'll end up being. Well, p will be. So here's Wald's argument in a nutshell. Suppose I want to determine this composite hypothesis of whether or not a random variable's parameter is above or below a threshold. Instead of doing that, I'm instead going to build a simple test where I'm trying to determine whether or not the parameter is equal to one of two values, where those two values are chosen around the threshold. Now, for these two values that are, for these two simple hypotheses, if I look back at that likelihood ratio, and I look at the sequence of all ones, it will confirm hypothesis 1. Right? So, as the actual value of the parameter starts to go a little bit further out towards the towards 1, that sequence that confirms the hypothesis 1 is actually becoming more likely. And so I can use the simple test to determine whether or not the parameter is above or below the threshold, even though it's not the parameter I'm looking for. And Wald has a nice argument that basically says this will work for basically any arbitrary sequence. And so that sequences that confirm one hypothesis or another end up becoming more or less likely as we look at parameters that are further and further from the threshold in either direction. So if the test that was going to test the simple hypothesis was going to say H1 for the actual value that it was testing, it would also say H1 for values of the parameter past the value it was looking for. Okay, so this is Wald's formulation, the Sequential Probability Ratio Test. And this is sort of my major tool that I'm going to use to figure out how to classify channels. There's a bit of notation, but really the only things that are sort of critically important is to look at this quantity in the middle. This is the likelihood ratio, but it's not the same likelihood ratio as the one we saw before. In this likelihood ratio, we make one of three decisions. If the likelihood ratio is above A, we declare H1. If it's below A, we declare H0. And if it's in the middle, we take another sample.
You said above A, below B.
Above A, below B, yes. Above A, below B, and if it's in the middle, then that's just sort of the critical part. If it's in the middle, we take another sample. And this taking another sample eventually will create a sequence that eventually crosses one of these thresholds. Wald argues that if you choose your thresholds like this, then you'll at most make alpha plus beta errors, and there's a bound on the sum of the errors down at the bottom. It's sort of Wald's standard result from 1948. Sorry, it's hard to see. So, to actually use the test, I do a little algebra plus some logarithms on that likelihood ratio we just saw, and I come up with these two threshold lines, and the sufficient statistic at the top called dm. And again, there's a lot of equations up here, but what's really going on is that dm is a random walk between two threshold lines. They're actually moving. The process looks like this. This is dm, and these are the threshold lines. So notice they're parallel. That's not an accident. The slope in this expression is exactly the same term, and the only thing they differ by is where they intersect. So as this random walk juggles back and forth, if it's stuck within these two thresholds, we keep sampling. The moment we find our first crossing time, or our stopping time, the big M, our test makes a declaration. It either declares H0 or H1, depending on where it walked out. Wald basically argues that if you walk out of this lower threshold or walk above this upper threshold, the probability that you shouldn't have is bounded by alpha or beta, respectively. So, how do I build a decision rule in general? If I'm talking about just an arbitrary observation space, a decision rule is nothing more than a function that for every observation I can think of assigns one hypothesis or another. That's what any decision rule does. Every decision rule has to chop up the observation space into things that confirm H0 and things that confirm H1. And so here, this coloration should sort of look like a decision rule. So why do I need decision rules? Well, it turns out the decision rule is actually the key element in a tool that I use to tune the sequential probability ratio test. And that tool is the operator characteristic curve. Now, this is very different from the receiver operator curve that most people are used to when you're looking at the standard EE text on detection. This curve is not the trade-off between alpha and beta. What this curve actually is the probability of declaring the null hypothesis given that the parameter is equal to a specific value. And it's basically just an integral of an indicator function. As you saw back here, the decision rule is nothing more than an indicator function on one of these sets. So, because of that integral, the operator curve has to walk through very specific points. And these points are these are sort of points that the operator curve must pass through. If I assume that the operator curve is continuous, I can derive this expression down at the bottom, which is the operator curve derived for the very specific case of Bernoulli random variables and sequential probability ratio tests as the decision rule. So,
James, I'm sorry. Go back.
Sure.
Of those four equalities, are the first two equalities or inequalities?
Where? Here?
Yeah,
These two?
LP1 and LP0.
Yes, they are equalities, and you'll see why in a second. That's actually coming up. So, so I can actually also simulate the operator curve by basically doing the sort of logical thing, which is pick a parameter, draw a sample, run the random walk through the test, and then when I run the random walk through the test, determine whether or not it declares age 0 or not, and then basically track a mean across trials to see whether or not it actually declares age 0 in the parameter that it's supposed to. That's basically what all of this equation is happening here. So this is the operator curve. And to answer your question, this is a fixed point, and so is this. And in fact, those points are fixed with equality from the integral. And the key point there is that that's exactly what we need to manipulate. Where we choose the P1 is where the point where this curve crosses through the value beta. Where we choose the P0 is where this curve crosses through the value 1 minus alpha. And in fact, this is how I'm going to use the curve. I'm going to use those points to tune this curve. You'll see that in a minute. So off the side again, another little bit of notation. The region between the points P1 and P0 is named the indifference region. The sort of key argument, the key understanding that Wald likes to give on this is that if I make a mistake by declaring a value is above the threshold when it's actually below, but that value is actually really close to the threshold, say for instance I declared 0.25 was below the threshold even though it was above, that's not a big mistake. I was off, but I wasn't off by a lot. On the other hand, if I declared that 0.5 was below the threshold even though it was above the threshold, that's a big mistake, and that's a serious error that I need to weigh very heavily. And so things that are within the indifference region, if you get them wrong, it's deemed not a big mistake. And things that are outside the indifference region, if you get them wrong, you want to bound the error that you'll make a mistake at that point.
So the dashed line is that function of P that you had on the previous graph?
So the dashed line is the
previous slide.
Yes. The red line is the simulated version of it, where the simulation was done basically by doing this process. You know, pick a sample, draw a random walk from it, run it through the threshold lines, see what it declares, do that over 1,000 trials, and then compute the sample mean of what was the probability of declaring H0 over that 1,000 trials. It seems to follow exactly. Right. This is sort of how I validated my my detector, by basically checking whether or not I could actually recreate this curve in practice.
But your simulation is just doing coin flips or something?
Yes.
Right, so it's kind of just checking that Wald was right?
Yes. Yeah, I'm basically verifying that I can write code that does what Wald says it will.
And you don't, like when you do simulations, do you have an upper limit on the number of experiments to hit a threshold?
I didn't sit down and calculate one, but I mean, I did.
But I'm saying you did not stop it, or do you have like an artificial stopping time, or you just let it go till it hits?
Well, I mean, I picked something so that the variance on measurements for each of the particular values of the parameter was going to get lower when I computed the sample mean of the trials. But there wasn't. I just basically just chose a large number for all the trials for each value of the parameter. So this is the thing we're actually interested in, the expected sequence length. This is the thing that I want to try to minimize, subject to the constraint that I don't have an error rate that's too high. And the thing that I want you to notice about this equation is that it depends on the operator curve. This is sort of very important because this is what it looks like, and what you learn by messing around with the equations and then manipulating the curves is that every time you adjust the operator curve, the expected sequence length adjusts accordingly. And you'll see that later on when I talk about parameterization. Right now, actually. So, in order to try to tune this this operator curve, I reparameterized points P1 and P0. I basically am measuring them from the center threshold, and so these two quantities, zeta and delta, are basically my sort of dirty trick for manipulating how the actual test works. What are zeta and delta? Zeta and delta. So this is zeta. It's the width of the indifference region, right? And as I increase the zeta, you'll see that that same indifference region with the same width just starts sliding in one direction or another. And so what zeta does is move the center of the indifference region, whereas delta makes the indifference region wider and smaller. So this parameterization helps me manipulate the operator curve by manipulating the threshold lines. This is how the threshold lines depend on delta. Basically, the smaller delta is, the bigger the threshold line, the wider the threshold lines are. This makes some sense, and you'll see why in a second. So the effect of delta on the operator curve is kind of hard to see because it's not very pronounced. It sort of turns that nice S-curve into a straight line. But it's the effect, these small nudges on the operator curve actually have a profound effect on the expected sequence length. For these little nudges down in the, I guess that's cyan, of the operator curve, the expected sequence length starts to jump up really fast, and the maximum gets really, really high. So why does that happen? Well, if we look back over here, as the threshold lines are getting further apart, it requires more samples to get out of them. And so by making the delta much smaller, I take a longer time to actually walk out. Just the minimum number of samples I need to get out of it is actually growing. But at the same time, because I'm taking more samples to get out, the probability that I make an error goes down. So I'm trading error probability for expected sequence length. Just sort of a natural trade-off. And this is sort of the same trade-off we saw when we looked at the variance equation because of that ratio of the random variables variance to the actual stopping time. This is what happens when you adjust the zeta. And the adjustment to the zeta is basically tilting the threshold lines. This tilt of the threshold lines basically trades off type 1 for type 2 error. And its effect on the operator curve is to slide the operator curve in one direction or another by moving that indifference region. And then what that does, and the key thing that this does for us, is it moves the maximum of the expected sequence length over to the side. Now you'll notice, unlike the previous curve where I got the delta much bigger, the difference between the maximum in the low zeta versus the high zeta is actually only about 20 samples, as opposed to 900. So this little jump in the maximum occurs because as the slope is tilting, the lines are also getting a little further apart. But there's more slope change than there is width increase. Whereas in this case, there was a little bit of slope change, you can sort of see it, but there was definitely a lot of width increase. So one parameter primarily tunes the maximum of the expected sequence length, and the other parameter primarily tunes where the center of that maximum is. Now, for our purposes, the expected sequence length of the parts we're going to actually deal with is usually based on the integral of this curve on the region we're interested in. So if we start sliding this curve over, we can actually get that integral to be a little bit lower while maintaining a bound on the error. So a dirty trick that a dirty trick that Wald and Sobel came up with that I used a lot was to actually use the same samples twice. So what this does is it basically partitions the interval into 3 regions: the good, the bad, and the ugly. And so we're getting towards the tool that I need, that first part of the stuff that I need, which is the sort of the classifier for a single channel that gets minimum samples, that can classify with a certain amount of error bound, but actually uses minimum samples. So this is what happens when you use 2 tests. You get 2 sets of threshold lines, 2 sets of hypotheses, and you need a combining rule that says, okay, well, if both of them declared above the threshold lines, then I'm going to say that this was in the high category. If both tests came below, then I'll declare this as the low category. And if one test set above and the other set below, then I'll say it's in the middle. And so this combining rule basically controls what kind of declarations I make, and actually also dictates how I make errors and how long my sequence is going to be. So this really is the sort of the thing that I need. This is the tool that will achieve low expected sample rate and while maintaining a bound on the error. So the operator curve for 2 tests is literally the operator curve for 1 test mirrored about the 0.5.
Excuse me.
Yeah?
Can you go back one slide?
Sure.
When you have a single test, you keep flipping the coin until it passes one of the threshold.
Yeah.
When you have 2 tests,
Mhm.
do you make a decision when the random walk passes one threshold?
Mm-hmm.
Do you make a decision at that point and consider it final, or do you wait until
both.
it passes the second threshold and you finalize both decisions?
You make, yeah, you have so back here, I sort of mentioned at the bottom, you have a combining rule that you have to wait for both tests to finish before you actually have a combining, before you can actually make a decision. So now, that's actually an important point, because what that does is affect our expected sequence length. And the expected sequence length just becomes the maximum of whichever one finishes last. Right? Because you have to wait for both decisions before you can actually combine them.
Do you find a substantial improvement in the quality of the joint decision by waiting?
No, I don't gain an improvement in decision. What I gain is an improvement in the granularity of my answer. That is, instead of saying it's definitely below 0.2 or above 0.2, I can say it's below 0.2, I can say it's above 0.8, and I can say it's in between. As opposed to low and not low. I can say low, high, and takes too long. Right? Okay, so now that I've got the first part, now I need the second part. I need some sort of a strategy for distributing measurements among channels. So what I'm basically going to do is I'm going to run one of these 2 tests for every channel. But I'm going to choose which channel I give measurements to based on how those 2 tests evolve. The rule for choosing comes from this cost function. The cost function basically measures, is an attempt to sort of characterize which of these channels is going to complete sooner. Which of these channels are the ones that show promise. The 2 key features of this cost function are these 2 terms right here, this projected distance and the cost penalty. Those are the 2 things that I'm going to have to manipulate. And so, what is the projected distance? Well, there are a couple of ways to measure your proximity to the threshold line. But this sort of graph sort of explains, or well, sort of shows what are the possible alternatives, right? You can try to compute the vertical distance, you can try to compute this Euclidean distance, or you can try to project out and see how long it will take you to actually get out under an ideal trajectory. It turns out that the ideal trajectory option ends up being the easiest to interpret, because you can measure how far you have to go in number of steps to complete. And this is sort of easier to sort of quantify than saying, oh, well, it's this many distance units in this graph, which is sort of an arbitrary measure. So, a few things to note about these different distance metrics is that as you go up in index, you also go up in complexity. Right? Computing the vertical distance is actually really easy, but not very intuitive. Whereas computing the projected completion time under an ideal trajectory is actually fairly annoying, or rather fairly computation expensive, but easy to interpret. It's sort of clear what that means. And then, because of that clarity of what the definition of the projected distance is, then we can actually figure out what our lambda is in terms of fractions of steps. So our hopping strategy, maybe I should probably not belabor this point, but our hopping strategy at every step is to basically just pick the smallest cost. And so this is the second thing that we need, a strategy that sort of dictates how to move around. And that strategy is compute this cost for every channel and pick the minimum at every time. It's basically a greedy strategy. So, so I sort of described how the projected distance works. Let's talk a little bit about what this measurement penalty is. So the measurement penalty, what the measurement penalty does is it controls fairness of distribution. If the measurement penalty is high, the distribution is more fair because channels have to have a cost buffer to prevent competition. Whereas if the measurement penalty is low, channels can generate more cost reduction than the measurement costs them to take. So this is a graph that sort of gives you an idea of what that means. This is the cost for 5 channels running this test with that cost function and the cost measured out in time. Now, starting from this end, you'll see that there's a little bit of sort of jitter going on, and then just from the beginning, the channel with the lowest parameter starts generating cost reduction that offsets the cost of measurement. And it does so very consistently. It basically pulls all the samples away from all the other guys. You'll see that all their costs are flat because they're not getting any measurements. Once this channel is done, its cost goes to infinity, and then they start fighting over the measurements again. And eventually, one of them takes over, but he doesn't really do a very good job, so he loses focus. And then we start to, this channel on the other side, whose parameter is also low, starts to pull away the measurements from the rest of his competitors. And eventually, he will complete, his cost will go to infinity, and then the rest of them just left duking it out. This is the low measurement cost regime. On the other hand, if I make the measurement costs high, then it's constant infighting. Everybody's always struggling to take measurements from everybody else, and because samples are so expensive, it's very hard to generate enough cost reduction to justify getting a sample in the first place.
Is this cost function something you created to make the system behave a certain way?
Yes. So the cost function. So actually, this is the sort of the important part of what the cost function does. You'll notice that the channels with the low parameters they get measurements first, and with this cost function low, they finish first. And so the thing that I wanted to do was prioritize channels with parameters that are low, push them to the front, give them samples first because they'll complete with fewer samples. And so if I push all the channels that have low parameters to the front and give them measurements first, I'll characterize more channels overall.
I guess like what you see here is that the first ones that finish are the green and the blue, and the green one is 0.1 and the blue is 0.9, and that's what you want.
Yeah. So the good and the bad come up in the front, and the ugly hang out in the back.
But if you're asking if it's a heuristic, it's definitely a heuristic.
Yeah, but I was just going to ask, is there a meaning to a cost function? Or
As opposed to it was the solution to some kind of an optimization problem that minimized something.
In other words, what's the insight into the cost
It's
function?
going to reverse engineer and figure out what's needed.
Okay.
Right. So to figure out how the system works, or to figure out how the system stacks up, we'll try to measure performance. And so performance will be measured sort of as the number of channels discovered. And this sort of goes to your question. It's sort of hard to write down a performance metric. And so most of the techniques that are like multi-arm banded and dynamic programming flavored techniques that build a cost function, they build a cost function by setting an objective and then working backwards and then saying this is the cost function that maximizes this objective. In our case, the objective of most channels classified is sort of hard to quantify in that respect. And so it's hard to write down a cost function that does that. So in our case, the things we're going to sort of measure, or the things we want to maximize, is the number of channels discovered. And the thing we're going to use as our constraint is a bound on the probability of error. And so,
but somehow discovering sooner is better than later.
Discovering, well,
is that what you just told us?
Sooner or more. Those are two different goals.
Okay.
So So the simplest classification scheme is just to take the number of samples I've got and the number of channels I've got, divide the number of samples by the number of channels, and then distribute that number of samples to every channel, and compute the estimate and bin them that way. Now, that's sort of annoying to describe, but this is what it looks like. So, I got, in this toy example, I'm allowed 26 measurements and I have 4 channels. So, 26 divided by 4 is a little over 6. I take the ceiling on that, and that's 7. And so, I just start from the left, put 7 measurements in the first channel, put 7 measurements in the second channel, put 7 measurements in the third channel, and then whatever's left goes to the fourth channel. Now, the trick here is that in this channel's case, I revisit the center many times. That's bad. I shouldn't do that. Because this channel's parameter is 0.5, and so I'm not walking away. This random walk isn't walking towards any threshold line. It's staying right where it started. And that is not what I want. On the other hand, in channel 2, or the black channel, this channel walks away from the center. And this is the desirable characteristic. And so, if my system was smart, it would pay attention to that channel more because it's walking away. Now, the purple channel is the one to watch, because that one is the one that is not glaringly, obviously misleading. It starts walking away, but it comes back, then it walks away a little further, then it comes back, and then it walks away again. Now,
why aren't those two symmetric? 2 and 7. 3.
Because,
well,
what do you mean?
you have a random walk that goes off towards probability 0. It's 0.5 or point. Oh, I'm sorry. Okay, so I read it. Right. 0.5 is in the middle. So.
Yeah, 0.5 is sort of hanging around the middle, and the other two are sort of shuffling off.
You didn't order them right.
You didn't order, yeah, that's right.
No, well, so that's the trick, right? As a user in the system, I don't know these numbers. They're there to label the channels, but I don't know them. I'm trying to discover them. Okay. So the big problem with that previous strategy was that it wasn't adaptive. It couldn't change based on the conditions we were dealing with. So this sort of exceedingly long slide that tells you how to build an adaptive tree scheme was something that we sort of cooked up just to see how an approximation of our scheme could work. Well, what does this tree scheme basically do? I'll describe it with a picture in front of me. What the tree scheme does is it sets aside a certain amount of samples to do a first pass. And then once it does that first pass, it computes the estimates of the parameter from that first pass, and then uses that estimate of the parameter to judge whether or not I should measure any of these channels again. And so, in this case, the number of channels, the number of measurements we're going to drop in each channel on our first pass is 4. And we're going to say, well, if we come back to the threshold, if we come back to the center 2 times, that's bad. We don't want to do that. So here we start with the first channel, and again it's the same channel, the same samples, so it comes back to the center twice. That's bad. We don't want to do that. This channel walks away and starts to turn back, but it hasn't actually returned to the center yet. So it's worth looking at again. Same thing with the one on the other side, and same thing with this one that's further away, the green channel. They all walk away from the center, and in the first 4 measurements they didn't come back, so I'm going to look at those channels again. So in the next pass, I now go to the channel, the black channel, and I'm looking at it, and it's doing the right thing. It's walking away perfectly. This is exactly what I wanted to do. Good job. I'll stick with that one. And for argument's sake, we're going to say that 8 samples is good enough, and it's characterized. We're done with that one. Now, for the purple channel misled me. It doubled back, and now you'll see at this point, it's crossed the center twice. It's done that bad thing that it wasn't supposed to do. So those 2 samples that come after that second crossing are kind of a waste. Because I sort of said, wait, you violated my rule, I'm done, I'm not coming back. But because my strategy is to drop 4 samples every time, I don't get to adapt. I at this point. I'm locked into this phase. So I'm going to put these four measurements in because I have to. That's what the policy says. And then finally I've got 2 measurements left, and I'll drop them in the last channel, and I don't know anything. That last channel is uncharacterized because I didn't get it. In contrast, this is what we propose. A system that dwells on a channel until it either fails to satisfy the criteria or finishes completion, or finishes characterization. Now again, we'll start from the left, and this one comes back twice. It's bad, we leave it. We'll go to the second channel. It walks away, and it does so in 8 samples, which is good enough. We're going to take that random walk and say, okay, great, that one's characterized. And now we'll move to this channel. Now, because we got unlucky, this channel lied to us. But when we got to the point where it came back the second time, we leave. Maybe we shouldn't have, but we did. And now, because we saved those 2 samples from leaving here, this channel, which is certainly going to walk away, because if you know the parameter, it's definitely going to walk away, it does. And it does what we want it to. So we managed to characterize all 4 because we were able to make this decision on the fly.
So the rule of stop when you have 2 crossings is also a heuristic.
Right, so that's just for this example. Right, that's not actually what the rule is, that's just sort of to motivate the this example. So in general, there's probably, there's a whole long section about choosing the rule the right way and tuning it for the appropriate balance on error, which is actually the thing we talk about. So, because we've got 3 bins, it now becomes a little harder to label what type 1 and type 2 error are. So I'm going to take a subtle cheat, which is I'm going to switch my hypothesis around and say that my null hypothesis is in the outer bin, and then if my null hypothesis is in the outer bin, then my alternate hypothesis is in the middle. And so I'm going to call type 1 errors, I said it was in the edges and it wasn't, and type 2 errors, I said it was in the middle and it wasn't. So this is the discovery rate for all 3 schemes. You'll see that the simple scheme does exceedingly well, way better than anybody else. In fact, it characterizes almost everything at the end. The only problem is, it also makes orders of magnitude more mistakes. So, clearly, we need to adapt a little bit at least. This is the tree scheme versus our scheme in discovery. Now, the tree scheme does better. It gets maybe like 15 more channels discovered. But what's the price we pay for that? We pay for that in error. Because the tree scheme doesn't adapt on a per sample basis, it makes more mistakes. And we saw that before when we could have left the channel, we didn't. So, if I had said that my bound was 5% error in mislabeling, then our scheme would have done it, and the tree scheme wouldn't have. And so the point being that for appropriate choices of the parameter, you can sort of tune the greedy scheme to basically achieve an arbitrarily low error. But if you tune it too hard, you'll end up having no answers.
So you're separating the number you classify from the from the probability of classifying correctly, and you're showing curves for both.
Right. So this is the number classified. Yeah.
But some of those are wrong in there.
Some
that classified.
Yes. So this is everything I figured out, and some of them may be wrong. And this is the probability that any one of the ones from that good set, that set that I've labeled as in the edges.
Like if you just looked at the expected number classified correctly, is there something, you lose something in kind of lumping them together?
Well, what is it, how bad is it to classify bad? I think that's where it is, right? I mean, what you're talking is something like good put, you know.
Well, yeah, I'm just asking, is it sort of physically, maybe you have to go back to look at, to say in terms of the context of the real experiment you're doing, whether that's a good option or Frederick says maybe that's a bad way to engineer your system.
So actually, I studied this a little in the thesis, but there's no slides on it here. The key thing to look at is your resource regime. That is, do you have a lot of samples and not a lot of channels, or do you have a lot of channels and not a lot of samples? So if you're in a place where you're resource rich, where you've got lots of samples and not many samples to go through, or lots of samples and not many channels to go through, there's no point in doing this. The simple scheme will work perfectly. It will achieve arbitrarily low error, and there is no point in actually trying to adapt to the conditions because you've got so much resources to begin with. On the other hand, if you're in the resource regime where you've got way more things to measure than you have samples to measure them with, you're going to have to make first the admission that you're never going to finish, and then two, some sort of compromise that says, if I can maintain a bound on error, can I at least get something? And this is what this scheme does, is it tries to get something in a regime where we know we're never going to get all the way to the end. And so if I can at least give you some small set of channels that is good, your strategy is already better off because you can start with the good set. And if that's bad, if that doesn't work out, you know definitely avoid the bad set. And if you have to, go to the ugly set.
I think Roy had a different question.
Slightly, but I'll go offline. I'm sure I'll have another question soon.
All right. Well, so the only other slide I have is this one, which says it doesn't come for free. Now, to sit down and actually compute the computational complexity is probably a little bit outside of my field of expertise, but a quick and dirty indicator is to just compute the loop time on trials of the simulations, and you'll see that our scheme has a linear growth in the number of channels that are in the time it takes to complete a loop versus the number of channels. And all the other schemes are literally in the noise. So the other stuff is much, much faster to compute. But you fail to actually maintain your error targets. And you really don't have a good way of controlling that. And so if speed is your concern, and you're willing to accept more error, then going with this sort of tree approximation to the technique that we're talking about is actually a way to go. But if you actually absolutely must have a certain bound on the error, then you're going to have to pay for it with both samples and computational cost. So, ways we can change this in the future. Well, one of the dirty tricks that I performed was I glued a lot of the hypotheses together by essentially exploiting symmetry. You don't necessarily have to do that, and there might be some ways to get around that and actually get better performance if you assume asymmetric hypotheses. And so you can choose your parameters in an asymmetric way and hopefully get some better performance. The other thing, the one critical thing that sort of really makes my system work really well is that I assumed all the parameters came from a uniform distribution. That need not necessarily be true, and we've seen some work in the literature about like compression sensing and stuff like that where maybe the parameters cluster. And so if the distribution of parameters is not uniform, then I'm in trouble. And things don't work out the way I expect them to. There are also lots of other sort of alternative techniques, and one can consider historical artifacts, like I always know this channel will be busy, so throw it out immediately, to possibly get some sort of better results. The idea is that this system should be in front of some other system, and so that the second system has better transmission capability. So I can try to incorporate my system with somebody else's to see what their effective throughput is. And of course, as with everything that talks about simulations, let's try it in real RF. Okay, fire away.